Swayam Prabha. Digital India. Educated India.
In doing statistical least squares, we found out the estimate that comes out of weighted least squares, where the weighting function is the inverse of the covariance matrix. We had already covered those areas. We covered the area under the assumption that the matrix H is full rank matrix. Now, I am going to consider a special case. When the matrix is full rank, the least eigenvalue must be positive, but when the least eigenvalue is very close to 0, then mathematically it is not singular, but practically is singular. This practical singularity, as exhibited by the minimum eigenvalue of the Gramian H transpose H, is because of the columns of H are linearly independent. They may not be totally linearly independent, but they will be theoretically independent, but practically not. So, what is the implication? If two vectors are such that the angle between them is very small, they are almost linearly independent. Mathematically, the angle must be 0, but practically the angle might be positive, but very small. So, that is what is called collinearity. If multiple vectors are collinear, then it is called multicollinearity problem. We have talked about least square problem z is equal to h of x. Now, I am trying to change the notation a little bit. I would like you to be able to visualize z is equal to x beta. So, the matrix H is played by the role of matrix X, the vector X is played by the role of beta. So, consider z is equal to x beta, this is m by n, this is n by 1, this is m by 1. So, what is that I am now going to consider? My h is my h is replaced by x, why not? Yes, I could have rewritten this in terms of h also, but I am going to redo it with x. So, so what is our starting point? I have a statistical linear least square problem, z is equal to hx plus v plus the noise v. V is a noise which is such that it is mean 0, its covariance of v is equal to r, and r is a SPD. R is a SPD. So, R inverse is going to be my weight matrix. I am now going to minimize f of x, which is equal to z minus x beta transpose, sorry, let me write that clearly, z minus x beta transpose R inverse z minus, let me write that down, transpose z minus. So, mathematically is the same, except that instead of h I am using x. So, let lambda 1, lambda 2, lambda n be the eigenvalues of the Gramian X transpose m, which is n by n. I am assuming m is greater than n. the smaller the two gramians. So, lambda 1 to the power half, lambda 2 to the power half, lambda n to the power half are greater than 0. These are the square root of the eigenvalues of the Jacobi, the gramian. So, these are called singular values of x. The condition number of the matrix X is the ratio of the largest singular value to the smallest singular value. This is a measure of the collinearity. We have already seen when two columns are collinear, the angle between them is 0, close to 0, they are linearly dependent. That will be reflected as the smallest eigenvalue will be close to being 0. 10 to the power of minus 12 is positive, but very close to 0. So, if the smallest eigenvalue is very small, the condition number is large. So, the larger the kx, more likely the matrix is singular, and this singularity arises from this multicollinearity. In other words, singularity of x transpose x can be measured by the condition number, which is the ratio of the largest singular value to the smallest singular value. In this case, I am going to go back to the spectral expansion or eigen decomposition. X transpose x v is equal to v lambda. This now becomes x transpose x is equal to v lambda v transpose. We have earlier seen the covariance of the estimate beta hat is equal to x transpose x inverse when R is an identity matrix. We have already seen that in the method of least squares, statistical least squares. So, if this is x transpose x is given by this, its inverse is given by the inverse of that, but we all know V is an orthogonal matrix, V inverse is equal to V transpose. We also know the product of the inverses is the inverse of the product of the inverses taken in the reverse order. So, that means A B inverse is equal to B inverse A inverse. By combining these two rules, you can readily see this becomes this, which this becomes this. Now, this can be written as Vi the row, this Vi is the column, Vi transpose the row, the outer product matrix. Each of the outer product matrix are scaled by 1 over lambda i's. So, this is the, now I want you to remember, this is the eigen decomposition for x transpose x, this is the eigen decomposition for x transpose x inverse, and this can be expressed as a sum, weighted sum of outer product matrices. If lambda n is very small, even small changes in the lambda n will reflect as big changes in the inverse. That means the estimate is very sensitive. Therefore, okay, one change in notation, instead of beta I should have said W. So, W is equal to beta. So, I am considering Z is equal to XW. So, instead of beta, please change it to W. So, W least square hat, this is the least square estimate of the weight. Now, please understand, originally I used the parameters to be X. I could have used the parameter to be beta. I could have used the parameters to be W. The row smells the same by whatever name you call. So, except for some slight changes in notation, everything that we have talked about continues. So, the least square estimate is given by x transpose x inverse x transpose y, which is the equation 31. So, what does this tell you? If this inverse is very sensitive to the data, now let us look at this now. What is x? X is the design matrix. X has the entries from the real world. If the columns of X are linearly, very nearly dependent, the matrix X transpose X is very nearly singular. The eigenvalues of X transpose X are functions of the elements of the matrix X. So, even slight changes in the elements of x will bring about great changes in the least eigenvalue. That means the estimates are going to be very sensitive. If estimates are very sensitive, it is very difficult to perform numerical computation, because in any numerical computation I am going to have a round of errors. So, sensitive computation in the context of round of errors will lead to changes that will be very huge. That will be very huge, and that could deteriorate the quality of the results. So, sensitivity of the solution is what we are now looking at, and the sensitivity of the solution is largely due to the smallest eigenvalue being close to 0. So, now we are looking for how do I reduce the sensitivity. I hope you are with me. So, let me quickly summarize. We did the least square modeling, is a statistical least square modeling. I have a noise, I knew the noise is mean 0 and covariance R. I am assuming the special case of R being equal to identity. I am assuming a special case where the columns of x may be nearly collinear. The impact of near collinearity is expressed as sensitivity of the estimate of the weights of sensitivity of the parameters estimates W hat LS is equal to x transpose x inverse x transpose y. And we just saw sensitive calculations are very difficult to do in computers, because even a small change in the data will lead to large changes in the estimate value, and that is not good from a computational perspective. So, we are now seeking methods by which I can reduce the sensitivity. One solution is to reformulate it as what is called the ridge regression. Ridge regression is essentially adding a penalty term. We have already talked about Tychonoff regularization, penalty function method in least square regression. And so, another term in here is called the ridge regression. So, I am going to reformulate the problem by changing the cost function. The ridge regression JRW is 1 over, I am assuming R is equal to sigma square I. Therefore, R inverse is equal to 1 over sigma square I. Therefore, this 1 over 2 sigma square comes in. So, what is my objective function? My objective function is equal to 1/2 of 1 minus xw transpose R inverse y minus xw. So, here z is replaced by y, h is replaced by x, and x is replaced by w. So, except for a change in the labels, nothing changes, and R inverse gives rise to 1 over sigma square. 1 over sigma square comes in. Sometimes I put a half, sometimes I do not put a half, and you should know why. For example, I have already told you, if f of x is a function, if I multiply f of x by a, if I multiply f of x by a plus c, so multiplying a function by a positive constant does not change the location of the minimum. Multiplying, adding a constant to a function only shifts the function up or down without changing the location where the minimum occurs. So, I can multiply a function and add a constant. So, all these three functions essentially have an invariant location for minima and maxima. And why multiply by half? These are quadratic functions. Quadratic function, the gradient of x square is 2x. Sometimes the algebra I have to bulldoze that number 2 all along. So, I would like to cancel the 2 as and when it occurs. So, dividing by 1/2, multiplying by 1/2 helps you to simplify the expression without additional constants to worry about. So, that is all what it is. So, 1 over 2 sigma square, this is the residual transpose, this is the residual, plus 1/2 of alpha times the square of the norm of W, square of the norm of W. So, this is called the regularization term, this is also called the penalty term, alpha is called the penalty parameter, alpha is a large penalty parameter. Now, if alpha is large, I am going to minimize it with respect to W. So, W is very sensitive. So, I want to be able to reduce the sensitivity by including this penalty term 1/2 of alpha W square, alpha of the square of the norm of W. So, the penalty term is called the regularization term. So, the gradient of this is gradient of GRW is 1 over 2 sigma square. Look at that, there is a 2, there is a 2, 2 gets cancelled, that is what I talked about. I equate this to 0, I get a new form of normal equation. So, this is the normal equation, x transpose x plus alpha I is equal to x transpose y. So, that gives you the estimate, the ridge regression based estimate, least square estimate is x transpose x alpha I inverse x transpose y. That comes from the ridge regression. This is x transpose x plus alpha I inverse x transpose. To make sense of this 333, so I would like to see how this insertion of alpha term is going to help you to desensitize. To do that, I am going to express x in SVD. So, to be able to x in SVD, x transpose x v is equal to v lambda, x transpose u is equal to u lambda. Therefore, x is equal to u lambda to the power half v transpose. Please understand, we did this when we did the statistical least squares. We have already done the ordinary least squares earlier. When we did the ordinary least squares, we have done method of matrix decomposition. We have introduced the SVD and other things. So, before you come to statistical least squares, you already know and fall back on the knowledge we have already done. So, x transpose s is equal to v lambda v transpose, v lambda v transpose v v transpose is I. They are orthogonal matrices. So, from here I can express my ridge estimate, which is x plus lambda. This is v lambda v transpose plus alpha v v transpose inverse u lambda to the power half v transpose transpose. So, this is exactly this expression with x replaced by SVD, x transpose x replaced by the eigen decomposition. So, that is essentially given by actually the lambda must be equal to alpha, forgive me, the lambda must be equal to alpha. Lambda is a parameter, alpha is a parameter. So, lambda must be equal to alpha. So, you could have v lambda v transpose alpha plus v v transpose this. So, v is the left common factor, v transpose the right common factor. We can take the left and right common factor, expresses like this, and this is the SVD. I am applying the transpose of the SVD to get this term from here, transpose of the product of the transpose of the reverse order. The inverse, now we already know v transpose is equal to v inverse, that is, and the product of the inverse is taken the inverse of the reverse order. So, applying those two rules, I get this. V transpose v is identity. So, that expression now reduces to v lambda plus alpha I inverse lambda to the power half u transpose. Now, look at that, this is the SVD of S plus alpha. S plus alpha could be thought of as the generalized inverse like thing. Now, look at this. Now, this is V, this is U transpose. This matrix that comes out, I am going to call this capital D. So, this reduces to V D U transpose, where D is the diagonal matrix, is the n by n diagonal matrix. The this is the diagonal matrix, this is the diagonal matrix, product of two diagonal matrices is the diagonal matrix. This is lambda to the power half is lambda I to the power half. This is lambda plus alpha I inverse, so lambda I plus alpha. So the diagonal element dii is equal to lambda I to the power half by lambda I plus alpha. Therefore, xi plus alpha is given by the summation lambda I to the power half lambda I plus alpha times vi ui transpose. This is an outer product matrix, the weighted sum of outer product matrix. Now look at this now. The addition of lambda I to lambda n. See, that's what is happening in here. Lambda n is the least eigenvalue. In the previous case, if alpha is 0, this term reduces to 1 over lambda I to the power half, and if lambda I is very small, lambda I to the power half is also very small, and that makes the sensitivity. So one way to desensitize is to be able to increase artificially by adding a quantity alpha greater than 0 to all the lambdas, and that's exactly what this term does. I want you to understand this. Alpha lambda plus alpha I, what is that? Alpha I is a diagonal matrix. This is a diagonal matrix. Adding a diagonal matrix to this, so this is called diagonal perturbation. Diagonal perturbation. So by adding a diagonal perturbation with a suitable alpha, I can reduce the sensitivity, which is the essence of the equation 36. Now I would like to be able to compare, to analyze the impact of this. Consider the special case when the columns of x are orthogonal. Look at this now. This is an opposite case. So the columns of x being orthogonal means they are linearly independent. The angle between any two vectors is 90 degrees. This is perfectly conditioned. So I am going to consider the perfectly conditioned with the ill conditioned. Ill conditioned means lambda n is closer to 0. That means the columns. So in one case, the columns of x are such that some of them may be collinear, multicollinearity. If the columns of x are orthogonal, that is the opposite of multicollinearity. They are perfectly conditioned matrix. Perfectly conditioned matrix. So the columns of x are orthogonal. That the x transpose x is n times I. N times I. That means consider the special case when the columns of x are orthogonal, that is x transpose x is equal to n times I. So in this case, the ridge regression W hat or LS is x transpose x plus alpha I inverse x transpose xw plus v, and that is equal to y, that is the observation vector. So if you substitute y is equal to xw plus v, you can distribute this x transpose inside. So this becomes this plus xxw plus x transpose v, x transpose v. But xx, I am assuming x transpose x is ni. So this is equal to ni plus alpha I inverse. This is niw plus x transpose x alpha I inverse x transpose v. Please understand what's being done in here. I am making a particular choice of x. I am making a particular choice of x. So this is equal to ni plus alpha I, niw plus the term coming from the noise. This term, when you simplify ni combined with this, it becomes n over alpha n plus w times w plus x transpose v divided by alpha n. Please understand, this term reduces to Ni alpha I, so alpha x transpose V divided by alpha plus n. This is an interesting derivation. So, the estimate consists of a deterministic part plus a random part. EV is 0. So, if I took the expected value, the random part expectation is 0. So, now the expected value is equal to W. Please understand, W is the unknown deterministic constant, is n over n plus alpha. N over n plus alpha is not 1 unless alpha is 0, but I have assumed alpha is greater than 0. So, n over n plus alpha is less, this quantity is less than 1 when alpha is greater than 0. So, my expected value, the estimate is not equal to W, but equal to a constant less than 1 times W. That means the estimate is biased. Wow! Until now we have seen least square estimates are unbiased, but the general problem of least square estimates may be subjected to computational difficulty if the columns of the design metric H, which is called X here, has a collinear property. The condition number is very large. To desensitize it, we included the penalty term that helped to increase the minimum eigenvalue so as to desensitize it. But what is the impact of it? It introduces bias in the estimate. So, here is where the whole saying comes in, you can't have it all. If you want to be able to address one question, some other problem pops up. So, what is the end result of this? Using the special case of x being orthogonal in the sense of x transpose is equal to Ni. Why do we assume the special cases? Because I want to bring the beauty of the analysis. The special cases are the one that helps you to bring the beauty of the analysis to the forefront. So, without the ridge regression term, it is unbiased. With the ridge regression term, I lose the unbiasedness, I lose the unbiasedness, a bias is introduced, but I help to desensitize. So, desensitizing is very important computationally. So, that means if you want to desensitize your calculation by introducing a penalty parameter, you have to live with unbiasedness. So, you have to live with the estimate being biased. You have lost unbiasedness. Unbiasedness is an important property. But I want to be able to compute, that means I am trying to compute the quality of the, I am trying to quantify the quality of the least square estimate using regression, using ridge regression as a function of the regression parameters. So, we already talked about two impacts. One, it introduces the bias. Second, it helps to desensitize. One we like, another we don't. One we like, another is not desirable. Now, I am going to compute the covariance matrix of the estimate. The covariance of the estimate for the special case when x transpose x is equal to Ni. The estimate takes this expression. Covariance, we already know covariance of x is the same as covariance of x minus E of x. This is the mean of that. So, if I subtract the mean, the covariance of this is equal to covariance of x transpose V divided by n plus alpha. The covariance of this is, if you multiply a random quantity by A, the covariance gets multiplied by A square. So, the covariance multiplied by 1 over n plus alpha whole square, expected value of this times that. I hope you are all with me. So, this is the vector, this is the row vector, this is the matrix. Now, X is the matrix which is deterministic, so they get out. So, this expression reduces to 1 over n plus alpha whole square x transpose expected value V V transpose x. We already assumed V is such that the expected value of V is 0, the covariance of V is equal to R is equal to sigma square I. That is the assumption we are carrying over. Therefore, from here you can see this expression now becomes sigma square Im divided by n plus alpha whole square x transpose x, Now, we already know x transpose x is equal to n times I identity. Therefore, this whole expression becomes n times sigma square by n plus alpha square Im, But we already know x transpose x is equal to n times I. I hope you are all with me now. Therefore, I is, so from here x transpose x inverse is equal to 1 over n times I. Therefore, I can be expressed as n times x transpose x inverse. So, by this using in here, therefore, now this becomes n sigma square by n plus alpha square x transpose x. Therefore, the covariance of the ridge based least square estimate is sigma square. Please understand that this is without ridge, this is with ridge. So, without ridge is sigma square times x transpose x inverse, which we have already shown in the module on statistical least squares. This is the covariance of the ridge. Sigma square x transpose they are common, but the ridge expression is multiplied by n square by n plus alpha whole square. Please understand, n square by n plus alpha whole square is less than 1 because alpha is greater than 0. So, that essentially tells you the covariance of the ridge based expression is less than the covariance of the ordinary least squares, since n square by n plus alpha whole square sigma square is less than that. That is essentially the argument I showed you again earlier. So, what does that tell you? The variance of the ordinary least square estimate minus the covariance of the ridge regression is given by this expression. Now, please understand, this are two common factors. If I took the common factor, I can essentially see this is the old unweighted variance without ridge. So, the ridge brings in alpha times 2n plus 1 divided by n plus alpha whole square. So, what does this mean? This means the covariance of the ridge estimate is smaller, but it is biased. The difference between the variance is greater than 0. Therefore, the ridge regression estimate has a lesser variance, but biased. This is called bias variance trade off in least squares theory. So, what is that we have established now? We have established an additional result for statistical least squares, namely, if the design matrix H, which is now called X, the observation instead of being called Z now called Y, the parameter instead of being X is called W. Again, this gives you an idea that how to change the symbols without having to change the concept. And why is this important? If you read different papers, different authors use different notations. So, you should be able to go from paper A to paper B to paper C, each of them different, using different notation, but they are talking about the same problem. So, you should be able to translate results from different papers in different notation and bring them under one common framework to understand, to desensitize you with respect to changes in symbols. Symbols are important, but symbols are not the ultimate thing. It's the interpretation of the symbol that is important. So that is one thing that comes out of the analysis. Second thing that comes out is that if I want to be able to desensitize, the cure is to be able to introduce a penalty term that is called the ridge regression. Ridge regression achieves one goal, namely it helps to desensitize. That means even small changes in the data set is not reflected in the estimate as large changes. It smooths the estimate. It is less sensitive to variations, and that is a desirable property. But introduction of the penalty term reduces the variance, which is again positive, but it increases the bias. I am sorry, it changes unbiased to bias. So here is a very nice trade-off. You solve one, you solve to address one problem, you get two end consequences. One consequence we like, another consequence we may not totally want it to happen. Please understand, our ultimate goal is to have minimum variance unbiased linear estimates. Blue. So U in blue, best unbiased linear estimate. We still have the best. We lost U, but the variance, while being least, is the variance is also now reduced. So I have more confidence in the estimate. The estimate has a bias. The problem is desensitized. So now you can see the various impacts of least squares theory, statistical least squares theory, with respect to bias covariance trade-off. So that completes our topic on bias variance trade-off. Thank you.